Okay. Yeah, thanks so much to the organizers for inviting me to speak. It's unfortunate that I can't be there in person, but it's nice to be there remotely. So I'm going to start with some background and motivations. And since this conference is about hydrodynamics, a natural starting point is to remind ourselves that conventionally in hydrodynamics, we study the late-time behaviors of quantities like thermal two-point functions in chaotic systems. So we study for some local operators, A and B, some object like this. And we find that at late times, such quantities show some simple and universal behaviors. And we also find, that we also know a very clear physical interpretation for this quantity, which is that if we perturb the thermal state slightly by some operator A, then the effect of that operator will decay with time as the state relaxes back into equilibrium. And so if we later probe the system with some operator B, it would feel the effect of A to a lesser and lesser degree at later times. Okay, and so depending on whether or not the system has conservation laws, we have different behaviors of this quantity, but essentially the late time behavior in a chaotic system is fully determined by just the symmetry properties of the system. And for the audience in this conference, we're very used to calculating such quantities on two copies of the system on some Schwinger-Keldysh contour, and we can consider various time orderings of this correlation function, and they're all essentially related to each other by some simple analytic continuation. But now if we consider the system on four copies, then some fundamentally new object appears called the out-of-time ordered correlator, which lives on a contour like this. And this object is not reducible in any way to two-point functions, but it also shows some universal behaviors across different chaotic systems at late enough times. And the physics that is captured by this quantity is fundamentally different from that is captured by two-point functions because it involves a different set of timescales. And it also captures a different physical property of the system, which is the growth of the size of the operator in physical space. Okay, so we'll discuss this growth of operator size in a little bit more detail later. But again, this quantity has a good physical interpretation and some universal behaviors in different classes of chaotic systems. So a natural question then, based on this progress, is what physical properties of a quantum many-body system are captured by higher point generalizations of the OTOC, such as this object, which lives on 6 copies of the system? So in particular, do these objects have some clear physical interpretation, like the OTOC? And do they show simple and universal behaviors across different chaotic systems? And not only are these natural objects to calculate by generalizing the techniques used for two-point functions and OTOCs, but they're also something that is really physically measurable. In fact, they have been quite recently measured in experiments on superconducting quantum processors by Google Quantum AI. Okay, so it's then very natural to look for some physical interpretation of this quantity. Okay, a second set of motivations comes from wanting to find some quantum many-body analog of classical ergodicity. Okay, so in classical mechanics, if we consider some few-body chaotic system, it's often characterized by the property of ergodicity, which means that if we start with some initially localized distribution in phase space, then under time evolution, as long as you consider some coarse graining, this initially localized distribution spreads out to fill the entire phase space. Okay, so just so you have a picture in mind, one example is the so-called standard map of quantum chaos. And in that context, we have some kind of map in phase space, which is defined by some relation like this. There's some parameter k that enters into it, and that determines whether this map is integrable or chaotic. So if the value of k is small, then under time evolution, if we look at the distribution evolved to some late time, we find that it hasn't spread out too much. So this blue distribution is the late time locations of these points. But if we instead consider some large value of k where the map is chaotic, then we find that these time-evolved points spread out to fill the entire phase space. And at some fine-grained level, the volume is the same as before, but if we coarse-grain the phase space cells, then we see that the distribution has filled the whole phase space. Okay, so this gives the intuition that things spread out over time in chaotic systems. And so a natural question is how we should characterize some analog of this spreading in phase space in quantum many-body systems. But of course, there isn't really a canonical notion of phase space in generic chaotic quantum many-body systems. So we're not going to find a direct analog of this, but one natural analog which people have considered is just the spreading of an initially localized operator in the space of degrees of freedom. Okay, so this means that if we have some initially local operator A, then under time evolution, it spreads out to fill more and more of the space of degrees of freedom. Okay. And we can define some very precise notion of operator size, which is essentially the number of degrees of freedom on which the operator is supported. And we find that the growth of operator size is related in a very precise way to the decay of the out-of-time ordered correlator that we just discussed. Okay, so this is discussed, for instance, in this paper. And so because we know that the OTOC shows universal patterns of growth, this growth of operator size also has some universal patterns in different classes of chaotic systems. Okay, but one drawback of using this operator size as a measure of chaos is that there are some dynamics which we do not think of as chaotic, which still lead to the decay of the out-of-time ordered correlator or the growth of operator size. So one sort of simple example of this, which might be familiar to some of the audience, is a random Clifford unitary. This is essentially some simple operation which maps an initially local Pauli string to some highly non-local Pauli string. But it's still, the resulting operator is still relatively simple. It's not a superposition over many Pauli operators. Okay, so this is a situation where the dynamics have a lot of structure, even though they lead to the growth of operator size. And so it's natural to ask if there's some more fine-grained notion of ergodicity in quantum chaotic systems, and then whether it involves these higher point OTOCs. Okay, so this is the question we'll address in this talk. And in particular, in this talk, we'll explore a different aspect of ergodicity in the Heisenberg evolution of operators. Our question will be, how much does the time-evolved operator spread out with time in the abstract space of all possible operators on the Hilbert space, as opposed to in the space of degrees of freedom on the Hilbert space? Okay, and we'll show how this question, so we'll make this question more precise and then show how it leads to a quantity called from free probability theory called the free mutual information. And we'll show how this free mutual information is related to higher point out-of-time ordered correlators. Okay, so the plan will be to start from this question of spreading in operator space, see how it leads us to the free mutual information. And then I'll outline how to derive a closed formula for this free mutual information. And then I'll discuss this general relation between the free mutual information and higher point OTOCs. And finally, I'll discuss the behavior of the free mutual information in various classes of chaotic systems and how it differs from interval systems. Okay, so any questions so far on this brief introduction?
Hello. So
Yeah.
this spreading of operator is your definition for chaotic system?
Yeah, and I haven't quite defined what I mean by spreading in operator space. So this is what I'll do next. Yeah. Okay. Great. So now in my question, which is about how much does the time-evolved operators spread out with time in the space of all possible time-evolved operators, I need to clarify what I mean by the space of all possible time-evolved operators, and then what it means for the time-evolved operators to spread out. So for the space of all time-evolved operators, I have in mind that if I have some initial operator A in some d-dimensional Hilbert space, then I want to consider the set of all operators that can be obtained by any unitary evolution of this initial operator. So I consider the set SA of all operators which can be obtained by any unitary in the whole d-dimensional Hilbert space, which can act on A. Okay, and so I'll need to talk about some notion of volumes in this set SA. And so I'll briefly mention what kind of volume I have in mind. So this group of all unitaries in d dimensions can be seen as some compact manifold of dimension d squared. And this set SA is essentially a manifold which is just as large. It has a slightly reduced dimension because some of these unitaries leave A invariant. So, but the dimension is still of order d squared, where d is the whole Hilbert space dimension. Okay, so if you have n qubits, then d is 2 to the n. And the way that I can quantify volumes in this set is, for instance, by using some measure like the Haar measure on the unitary group, and then looking at the measure that induces on this set SA. Okay, so this is the technical detail, but it's just to keep in mind that there's some concrete definition of volumes on this set. But we can visualize this set.
Can I ask a question? So
yes.
I would have thought that this space is some dense. This the orbit, the orbit of A under all unitary transformations. Could it not be not a manifold at all, but some dense set in some, it could densely cover some manifold. I'm just going by some classical intuition. You start with A, and so this manifold could have some weird structure. It could be just densely situated in some actual manifold, but otherwise it could be just infinite.
Oh, so are you thinking about the actual evolution of A under e to the minus IHT for some fixed Hamiltonian as a function of time?
I see. You're saying that if I consider all possible unitary operators, then what I'm thinking may not be right.
Right, because I think this is just a matter of definition, and I'm choosing to define the set as the set of conjugations by all unitaries in the d-dimensional unitary group. So in that case, it is a smooth manifold, which is just like some quotient of u of d.
Got it. Thanks. Yeah.
Yeah. Great. Any other questions? Okay. So so to visualize this even more explicitly, so we can imagine discretizing this set SA. So here I've drawn a sphere, but I want you to imagine a sphere in of order d squared dimensions. Okay, so if I discretize it with any metric, the specific metric doesn't matter too much. I'll get some number of grid points on this, and the number of them will be proportional to whatever distance epsilon I chose, so 1 over epsilon to raised to the power of d squared. Okay, so this is some number of operators, which is doubly exponential in the number of degrees of freedom, because recall that d was, say, 2 to the n in some qubit system. Okay, so this is just a very large and completely different space from the space of degrees of freedom. And okay, so now we want to ask questions like, what is the fraction of the volume of the whole set SA that is occupied by the time-evolved operator? Or what is the fraction of elements of this discrete set that is that the time-evolved operator is close to? Okay, so these are just discrete and continuous versions of the same question. But as I've stated them so far, the answers are just trivial, because A of t is just a single fixed operator. So of course, it just occupies 0 volume and is close to just the set operators in 1 epsilon net. If that's really how I'm going to define the time-evolved operator. Okay. So in order to get some meaningful notion of spreading, I need to coarse grain A of t in some way in order to associate some larger set with the time-evolved operators, so that I can talk about some growing ratio of volumes. Okay. So in this talk, we'll choose a particular way of coarse graining the time-evolved operator, which is inspired by the maths of free probability. But I'll try to motivate that it also has a natural physical interpretation. So, so we'll define our notion of coarse graining with using some reference operator B, which is some simple operator that we know, and some reference state rho. Okay, so rho ideally would be something like the thermal state, but in most of this talk, we'll just take it to be the maximally mixed state, so infinite temperature. And then the idea behind the coarse graining is to forget the full Hilbert space description of A of t, and remember only some limited amount of information, which is the set of expectation values of all possible sequences of A and B in the reference state row. Okay, so all possible correlation functions of this kind for any integers mi and ni, and any number of such sequences. Okay, and we refer to this data as the joint moments of A of t and B. And we'll define the coarse-grained set of A of t conditioned on B as the set of operators within this whole set SA, such that the joint moments of A tilde and B are the same as the joint moments of A of t and B. Oops. So we're requiring that we consider the set of all A tilde which can match these correlation functions, even if their exact Hilbert space description is not the same as that of A. Okay. And one reason why this might seem like a natural coarse graining procedure is that we do something similar when we talk about, say, considering some coarse-grained entropy associated with some pure state. We consider all possible other states which can match all simple correlation functions within the original state and then maximize the entropy over all such states. So this is just to motivate that coarse graining based on correlation functions is a very natural thing to do. And in this case, we consider the set of all possible out-of-time ordered correlation functions. Okay. Okay, cool. So this set SA of t of B is now our coarse-grained set of operators for A of t with respect to B. And now we can precisely state our question about the spreading of A of t in SA by asking, how does this ratio of volumes of this coarse-grained set, which is time-dependent, to the volume of this whole set SA behave? Does this ratio grow with time, and does it approach 1 at late times in a chaotic system? Okay. So is the setup and the question clear? Okay. Cool. So the quantity that I'm calling the free mutual information is essentially equivalent to this ratio of volumes. It's defined with a minus and a log. And one reason why it can be thought of as a mutual information is because I can write this quantity. If I go back to my discretized picture, then I can see it as a difference of the number of operators in the whole set SA minus the number of operators in the set SA of t conditioned on B. Okay, so this first term can be seen as some kind of entropy, or like it can be seen as a way of quantifying my uncertainty in what A of t is, if the only thing I know about A of t is that it was obtained by some unitary evolution from the initial operator A. And I don't know anything else. Okay, and the second term is the number of possibilities for what A of t can be. If I know not just that it was obtained from unitary evolution by A, but I also know the set of its joint moments with some operator B. Okay, so this second term can then be seen as some kind of conditional entropy. And so a difference between the whole entropy and the conditional entropy is a mutual information. So one thing that we can just see immediately from this definition that would be useful to remember is that as just because of this minus log, as the volume fraction increases from 0 to 1, that corresponds to a decrease of the free mutual information from infinity to 0. And one way of interpreting this second way of writing it is that this quantity is capturing sort of how much knowing the relation between A of t and B allows us to compress the description of A. Because essentially the description of A, if you don't know anything about B, is just that I have to tell you exactly which element it is of this set SA, whereas I can compress the description by telling you which one out of a smaller number of possibilities it is if I tell you about its relation with B. Okay. And then another sort of comment is that this can be seen, there have been various approaches to trying to define some kind of mutual information across time. And this can be seen as a new version of a mutual information across time, in the sense that it's the most natural notion of mutual information associated with two non-commuting operators. So the usual difficulty with describing some density matrix across different times is that the operators at different times don't commute. And so the most general way of describing the joint distribution of two non-commuting operators is exactly in terms of this set of moments. Okay. So in that sense, this is a natural notion of mutual information.
Sorry, Shreya, maybe I have missed it. So is the choice of B important?
The choice of B, so we'll see in actual examples when we compute whether it's important or not. For now, we should just think of it as some simple reference operator. And I guess we should expect that if we have some chaotic system, then the specific choice of the reference operator shouldn't matter too much. And we do see that in practice.
Thank you.
Okay. So just a brief comment. So this quantity, which we have defined in this with this physical motivation, is closely related to a mathematical quantity called the free mutual information, which appears in many papers by these authors. But our physical setup is somewhat different from their mathematical setup because essentially we have to consider a setup with large but finite dimension d, and also some fixed time evolution operator. So their definition doesn't quite apply. And in particular, one difference is that we can't actually consider, we have to introduce some notion of a cutoff, both in like the degree to which we match these moments. So there will be some approximation delta, which we can't quite take to zero in the matching of these moments. And also we can't quite take arbitrarily high moments. We need to put some upper cutoff on sort of the maximum number of powers of A and B that appear. Okay, but so this is where like a lot of work in adapting the mathematical literature to our setup goes. But for large dimension, we can choose n large enough and delta small enough, scaling with the dimension in a certain way, such that at leading order, the free mutual information ends up being independent of these cutoffs, which is why in this whole discussion so far, I haven't explicitly mentioned these cutoffs. Okay. Okay, so we've defined this quantity, but now we would want to see whether it actually physically has the meaning that we want it to have, and whether it actually decays with time if you have some actual chaotic system. But before we do that, let's check as a sanity check two extreme limits. Okay, so firstly, if you consider the case where A of t and B commute with each other, then in that case, essentially, the operator A of t is forced to be block diagonal in the eigenbases of B. And that makes the sort of manifold of possibilities for what A of t can be much smaller. It makes it some finite codimension manifold within the whole set of SA. Okay, so it ends up being measure zero. And in that case, the volume ratio is zero and the free mutual information is infinite. Okay. We can also consider an opposite limit where we take the time evolution operator to be a typical instance of a H-random unitary. Okay, so we just draw a H-random unitary from U of D, and we generally have the understanding that this is sort of the most maximally scrambling or chaotic operator that one can have. And in this case, if we take the limit of the dimension going to infinity, then these existing mathematical references that I mentioned imply that the free mutual information between A and say the time evolution of A by this H-random unitary is zero. Okay, and A and the time evolved operator are so-called freely independent random variables in this limit. And I'll go into a little bit more detail on what free independence means. But essentially, in the most chaotic case that we can think of, we find that the free mutual information is zero. And in the case which is very non-generic, we find that it's infinite. So this is consistent with our intuition that the free mutual information should decay from infinity to zero in some physical system. Okay, but of course, to come close to actual physical systems, we need to consider cases with finite Hilbert space dimension and some continuous time evolution operator instead of a H-random unitary, and also some locality of interactions, and see if this is still true. And in these cases, we can at best have some approximate freeness. So In what we want to do is consider cases where A and B commute at t equal to 0 so that the free mutual information is initially infinite. And our main question for the rest of the talk will be whether this free mutual information decays with time in any actual chaotic system. Okay, so, but to address this question, we need some more explicit formula than what I've told you so far, because this ratio of volumes on the unitary group by itself doesn't look like it can immediately be computed. Okay. So the first thing I'm going to do is briefly mention how we can derive an explicit formula for this free mutual information. And we can do this in a case where A and B both have the spectrum of Pauli strings. So in particular, we can take them to be two Pauli strings, which is one very natural choice. So A is the initial operator here. Or we can take them to be arbitrary unitary conjugations of Pauli strings. So the only property that we use of Pauli strings is the fact that they square to the identity and they're traceless by themselves. Okay. Okay. So in this case, because of these properties that I just wrote, the full data of all the joint moments just reduces to a simpler set of moments, which are labeled by one positive integer n. And they're just a set of these objects, trace of A of t times B to the power of n. Okay. And now we want to identify the elements A tilde of the coarse-grained set, which satisfies the condition that trace of A of t times B to the n is approximately equal to A tilde times B to the power of n. Okay, so some more work needs to be done in the case where there's actually some small difference between the two sides. But to get some intuition, we can just consider the limit where we require all the moments to match exactly. And then we can immediately see that this condition is equivalent to requiring all the eigenvalues of A tilde times B to match the eigenvalues of A of t times B. Okay. So the eigenvalues of this fixed operator A of t times B would be some eigenvalues which live on the unit circle, essentially because this is a unitary operator because of the set of A and B that we're considering. And we want to find the set of A tilde B that can match all of these eigenvalues. Okay, so we're interested in this ratio of volumes, and because we're, as I mentioned at the beginning of the talk, we're using the Haar measure for volumes in this set SA. So with by looking at it a little bit, you can convince yourself that this ratio of volumes actually maps to a probability under Haar random unitaries, that the eigenvalues of UA, U dagger B are equal to these fixed set of eigenvalues of A of t times B. Okay. And the probability distribution for this object under Haar random unitaries can be worked out. And as is often the case, this probability distribution involves some van der Waals determinant. Okay, and essentially as a result of that, we end up with a simple Coulomb gas formula for the free mutual information in terms of just the real parts of these eigenvalues of the operator A of t times B. Okay, so it involves this log of the differences in the real parts of the eigenvalues. And it's some very explicit formula. And in particular, if you do a more careful analysis, then you find some dependence on the cutoffs n and delta that I had mentioned before, but they all go into this subleading part. Okay, so at leading order, yeah.
So we did not find here A tilde explicitly.
Yeah, we wanted to find the volume of the set of A tildes. Because there would be some large number of A tildes, and we essentially want to count them. So this is like the volume of the set of A tildes.
Okay, thank you.
Mm-hmm. Mm-hmm. Yeah, so A tilde is this UA U dagger that appears in this expression.
I have a question. So
yeah.
was A of t times B a unitary operator?
Why is it a unitary operator?
Yeah.
So that can be seen essentially from a combination of the fact that A and B are both Hermitian and unitary. So that is just a consequence of the spectrum of A of t and B.
Oh, because we chose them to be Pauli strings. I like the spectrum.
Yeah, exactly. And even if we don't choose them to be exactly Pauli strings, as long as they have the eigenvalues of Pauli strings, this would still be true. Great. Any other questions? Okay, great. So now we have an explicit formula, and this is good because in many cases, at least numerically, we can calculate it. And one thing we can notice about it is that the only case where it's infinite is if there are degeneracies in the spectrum of A of t times B. Okay, and otherwise, if there are no degeneracies, then generally it should be finite. Okay, so good. So now we want to, so far we have used the higher point OTOCs in our definition of the free mutual information, because essentially they were used in the definition of the coarse graining set. But there are some hints that even the exact values of the higher point OTOCs should be or might be related in some simple way to the value of the free mutual information. Okay, so in particular, the values of these higher point OTOCs are useful for diagnosing exact freeness of two random variables. So, in the earlier discussion, I mentioned this notion of freely independent random variables. And in general, the condition of free independence means that you can express the joint moments of, say, the freely independent variables P and Q in some simple way in terms of the individual moments of P and Q, which is explicit and involves certain non-crossing permutations. But in particular, in the case where P and Q are both traceless operators, the condition of free independence becomes very simple, and it just corresponds to the fact that all of these endpoint correlation functions of this form are equal to 0 for all n. Okay, so this can be seen as the definition of free independence for two non-commuting variables. And as I mentioned earlier, this is also equivalent to the fact that the free mutual information between P and Q is equal to 0. Okay. And based on the fact that these out-of-time ordered correlators are all exactly 0 in the exactly free case, this has also motivated the study of the behavior of these higher point OTOCs by these many authors, and they've studied and characterized the behavior of these quantities in a variety of different systems. Okay, but somehow there's a large number of these observables, and it's not exactly clear what we should be looking for in them or how to combine all of them into some single measure which tells you about the approach to freeness. Okay, so a natural question is whether we can relate the value of the free mutual information to the values of the OTOCs. And as I just mentioned, we know that there is this relation in the case of exact freeness. So is there some robust version of this statement? And it would be very useful if such a statement existed, because the free mutual information has a clear physical interpretation. And in particular, and that is the physical interpretation that we've been discussing throughout this talk in terms of this spreading in operator space, whereas the individual OTOCs by themselves don't have a very clear interpretation. And on the other hand, the usefulness would also go in the other direction, because the nth OTOC is often easier to calculate than the spectrum of this operator A of t times B, right? Because we know how to calculate them by using various kinds of Schwinger-Keldysh techniques and other methods in various examples of chaotic systems. And as I mentioned earlier, they've also been explicitly measured in some experiments. Okay, so then given that the OTOCs are easier to calculate, this would help infer the value of the free mutual information. And in fact, we find that if we start from the Coulomb gas formula that I had mentioned earlier and use certain resolvent techniques, then there's a relatively simple way to derive the fact that the free mutual information can be related to a sum over all higher point out-of-time ordered correlators. With this overall, so we find a sum of squares because this is a positive quantity, and some overall weight of 1 over p. Okay, so even though the free mutual information was essentially defined in terms of these OTOCs, it's kind of remarkable that the relation between the two quantities turns out to be so simple. Okay, so one quick consistency check is that at t equal to 0, all of these OTOCs are equal to 1. And so in this case, the sum on the right-hand side diverges. And as we discussed earlier, the left-hand side also diverges. Okay, so now we can ask questions about the time evolution of both sides of this and the individual OTOCs versus this cumulative sum in a variety of different chaotic systems. Okay, and we can ask about the various timescales that appear. And intuitively, whenever A of t and B have some overlapping support in some physical system, it's unlikely, unless you have some very special situation, that there would be some accidental degeneracies in the spectrum of A of t times B. So this suggests that at late enough times, the left-hand side should be finite. And so that puts some non-trivial constraint on the right-hand side and on the precise way in which this sum should converge. So in particular, you need at least some weak decay of the envelope of these endpoint OTOCs with P in order for the sum to converge. Okay. Okay. So yeah, great. So at this point, let's just calculate this and look at the behavior in various systems. So we considered a few different models for chaotic systems. You can consider random GUE Hamiltonians. The advantage is that in this case, at least the nth OTOCs are relatively analytically tractable. But the disadvantage is that these models have no locality. So they're not necessarily very good models for physical systems. And then another system you can consider is a random unitary circuit, which does have locality. But in this case, we can have only some partial analytic control over the nth OTOC. So the statements we can make are somewhat weaker. And finally, we can consider the case of chaotic spin chains, which is nice because it has both locality and energy conservation. So it's approaching some more physical system. And in this case, we can get some very explicit numerical results for both the Coulomb gas formula for the free mutual information and the nth OTOC. Okay, so before looking at the specific models, let me summarize what the results will be. So essentially, we find that across all three of these different models, we find that the initial decay of the nth OTOC is faster for higher ends. And because of this faster decay for higher ends, we find that the free mutual information starts to converge and decay on a similar timescale to the usual OTOC. And in fact, even a little bit earlier in the Hamiltonian case. Okay. And then when we look at these individual nth OTOCs for n bigger than 2, we find that they show oscillations as a function of both the time and the parameter n. And in particular, these oscillations with time kind of indicate that by themselves, these nth OTOCs are not very good physical probes of the approach to late time chaos, because we expect that the system is somehow monotonically approaching an increasingly scrambled state. So, but when we look at the free mutual information or these partial sums of the OTOCs where we truncate to some finite value, then we find that in all of these chaotic systems, these quantities show a monotonic decay with time. Okay. Good. So, so just to show some explicit plots. So firstly, in the case of random GUE Hamiltonians with no locality, we find that all of the OTOCs start to decay immediately for any operators A and B. And then in this plot, for instance, so both of these plots are the same, but the left one is for a longer time scale and the right one is zoomed into earlier time scales. So the black plot is the Coulomb gas formula for the free mutual information. And these various colors are sort of the cumulative sums up to increasing and max. And we find that beyond a certain time scale, even the second or the usual OTOC is enough to approximate the free mutual information. But in earlier and earlier times, we need to include information for more and more of the higher point OTOCs. Okay. So, but all of these partial sums show a monotonic decay with time, which is not the case if we look at the individual OTOCs. We find that for higher, so these are just two possible different choices of the combination of A and B. But in all cases, we find that the higher ends will initially start to decay faster. But then eventually the higher ends show worse and worse oscillations at earlier and earlier times. Okay. So as I mentioned, one of the nice things about this model is that one could hope to actually get some analytic formula for the free mutual information, because we can calculate these nth OTOCs. And in fact, calculating the nth OTOC is a little bit non-trivial in this case, but it can be done by using some other techniques from free probability. And so we were able to find some explicit expressions. But the only thing I want you to notice about this is that the expressions have more and more terms as n increases. And it's not quite that you can neglect some subset of these terms. So really, all of these terms are important, which makes it hard to somehow imagine how exactly we would sum overall n's to obtain some explicit formula for the free mutual information. But I think that is a good goal. So this could be one analytically tractable model, or perhaps some simpler version of this. Okay, so this is the result for the GUE model. And one might wonder if somehow the faster decay with n of the higher OTOCs is some artifact of the non-locality of this model. But from both of our other examples, we'll find that it's not. Okay, so let me briefly mention the case of random unitary circuits.
Shreya, you have 5 minutes.
Okay, perfect. So in the case of random unitary circuits, these are probably familiar to a lot of the audience. They're essentially some very simple model for a chaotic spin chain system, but it lacks energy conservation, and each of these unitaries is drawn randomly from the unitary group on two sides. And in these circuits, there's some parameter VB, which is the characteristic velocity at which information spreads in the system. And it's determined by the local Hilbert space dimension Q. And in the case of the usual OTOC, so the n equal to 2 case, these papers did a very nice explicit calculation of the second OTOC and found that it has this kind of simple behavior close to the front of the operator, or close to V equal to VB. So here V is just x divided by t. And in particular, you find the structure with some broadening of the cone, light cone of the operator, with some diffusion constant d, which is also determined by Q. Okay, but so for the higher n case, the calculation is much messier. And in our calculation, we had to make many assumptions about the validity of some membrane picture for higher n's, which, those conjectures are not foolproof and should be verified more carefully. But we essentially used this membrane picture for higher n combined with some combinatorial structure of this quantity, and we found, based on that, we found a structure that's consistent essentially with the faster decay of the higher OTOCs when they initially start to decay. Okay, so the main point here is just that there's a natural way in which this n appears in the exponent from the random circuit calculation. Okay, so if we consider the case of a chaotic spin chain, so we consider this usual case of the mixed field Ising model at some chaotic values of the parameters, then we can get sort of very clean numerical results. So we consider two operators which are at some separation. And so the initial time at which the usual OTOC starts to decay is around here. And then again, we find that the higher OTOCs initially start to decay faster. So this right plot is for the nth OTOC. And again, we find that as n increases, the decay times, the initial decay is faster, but then the higher n's also show worse and worse oscillations at earlier and earlier times. So this structure is essentially exactly like the GUE model, but just shifted to the right because of the locality of the system. And in this case, again, we find that even though the individual OTOCs show some large oscillations, if you combine them into this cumulative form, then there's some monotonic decay as a function of time of both the cumulative sums and the free mutual information. Okay. Okay, so now let me briefly discuss a couple of examples of non-chaotic systems. So the example that we started with as motivation for why the OTOC doesn't always capture the distinction between chaos and lack of chaos was the Clifford unitary case. So random Clifford unitary is just one which takes some initial Pauli string and maps it to some random Pauli string, which generically is very large. And in this case, the size of the operator grows. And in the value of the second OTOC is identical to the value for her random unitary. So it's very small. And this has to do with the fact that Cliffords form so-called 3 designs. But if we look at the behavior of the free mutual information, we find that it remains infinite after applying the Clifford unitary. And in terms of the OTOCs, the source of this is that every 4th OTOC just doesn't decay at all and just remains 1. Okay. And then another example we can look at is the so-called PFC ensemble, which has some additional operations in addition to Clifford's. And by some measures, it's more similar to a random unitary than a Clifford. But we can still find examples in this case where the free mutual information remains infinite for all times. Okay. And then another example of an integrable system we can consider is free fermions, where essentially for a slightly different reason, we find again that the free mutual information is infinite for all times. So essentially it's because there are always large degeneracies in the spectrum of this A of T times B operator. And here at the level of individual OTOCs, we can see that there are oscillations and they visually look worse than the case of the chaotic system. But a sort of even more concrete qualitative distinction is that even when you make these cumulative sums out of the OTOCs, you find that there are some oscillations in that as a function of time as well. Okay. And then we briefly considered also the case of an interacting integrable system. And in that case, we found that the results were actually similar to the chaotic spin chain. Okay, so just to summarize, we introduced and interpreted the free mutual information as a natural measure of spreading in operator space. And we gave an explicit formula as some kind of Coulomb gas potential. And we also related the free mutual information to a sum over higher point OTOCs. And we saw that this free mutual information has some universal decay in chaotic systems and does not decay in integrable systems. And then some questions for future work would be to generalize all of this to finite temperature, which is much more non-trivial, and to see the effects of energy conservation and other conservation laws, and to understand the connection of this quantity to various notions of operator complexity, and also to have a better sort of microscopic understanding of exactly what is the mechanism why this nth OTOC decays faster for higher ends. So yeah, that's all I wanted to say. Thank you.
Thank you, Shreya. So are there questions? Rushikesh.
Hello.
Yeah.
So what is the physical interpretation for these oscillatory OTOCs at higher end? Why we are getting oscillations?
Yeah, that's a good question. I don't have much intuition for why we always see these oscillations, and that has partly to do with the fact that I don't know what the physical interpretation of the individual OTOCs is. So the only kind of useful thing that I can say about that for now is that these oscillations end up not appearing in the in these cumulative sums for which we do have a good physical interpretation. But yeah, I think it is a good question, and I don't really have an answer to it.
Yeah. Thank you.
Any other? Yeah.
Hello.
Yeah.
Does this affect the Lyapunov exponent bound on the chaos proposed by using OTOC? So the multi.
So I guess I don't know if there is an. So you mean whether the oscillations affect that? Does any of this?
Where they show that that bound can be broken in certain cases. So can this be a test to see that?
So I guess there would be a number of steps before that. So one issue is that bound applies at finite temperature. And we don't, we can guess that there's some finite temperature analog of the free mutual information, which is related in the same way to finite temperature OTOCs. But we don't really know whether or not such a relation exists. And I'm not entirely sure. I think there are some papers on some analog of the chaos bound for higher point OTOCs, but I'm not familiar with exactly what the results are.
Okay. 2 more questions. We're running slightly late. Yeah.
Hello. Yeah. So first is do these oscillations, like they are more spread out, I think, in OTOC2, right? Like the most going for the furthest time for OTOC2, I guess.
Yeah, the OTOC2 doesn't quite oscillate. It kind of decays. And then there are some oscillations around the saturation value, but those are not very, those are probably some finite system effects.
So I got it all around. But okay, so my question was, if I want to interpret this for some emergence of some sharp light cone type structure, then does your result basically say that, okay, if you only look at OTOC2, then you are done?
No, actually, this is kind of showing the opposite. So the OTOC2 is the dark blue curve here. And the fact that these nth OTOCs keep moving earlier and earlier for higher ends is kind of reflecting the fact that there isn't a sharp light cone in this Hamiltonian system. So they're kind of reflecting this leakage of, like the small leakage outside the light cone. And so in particular, like in this plot, so this black curve is like from the Coulomb gas formula for the free mutual information. And the way that I've drawn it here, it looks like it becomes finite at this time. But that actually has to do with, like I had these logs of differences in eigenvalues. And the fact that it looks infinite before a certain value has to do with the cutoff that I put in this eigenvalue difference. So if I had like a higher numerical precision, then I think this curve would be, would have some finite value all the way up to 0. So all of this is showing that in the Hamiltonian case, unlike this random circuit case where there is a sharp light cone, so you should expect that the free mutual formation is infinite for V greater than 1 and then becomes finite for V less than 1. There isn't really a sharp light cone in this Hamiltonian case.
Okay.
And the VB that you would define based on the second OTOC would be different from the VB that you would define based on the nth OTOC.
Okay, the last question, short one.
Okay, so I have a naive question. You were trying to see if free mutual information is a useful measure to see if there is chaos in a quantum system. So what is the definition of chaos that you were using?
So I guess there can always be like many different definitions of chaos, and it's not really ever clear how they're related to each other. And in this case, I guess I'm defining chaos as through examples of chaotic systems, and then checking that in examples of systems which I think of as chaotic, like the chaotic spin chain and random GUE and random unitary circuits, I do find a decay of this free mutual information. So I'm not starting from some rigorous definition of quantum chaos. But I find that that the decay of the free mutual information is consistent with my intuitions about chaos.
Okay, thanks a lot, Shreya, for an excellent talk.
Yeah, thank you.
Our next speaker is Takato Yoshimura.